Well, as So said, I'm going to talk about spin transport through antiferromagnetic insulators. And this work is about to be published in PRL. It should be actually any day now, but it's currently up on arXiv if you want to check it out. And this is done in collaboration with a couple of our colleagues in Norway, namely Hans Skarsveg, whose name I'm totally mispronouncing. So sorry, Hans, if you see this. And Arne Bratas, both of who were at NTNU in Trondheim. And of course, Rembert Dana, who's my supervisor at Utrecht. OK, so first, let me start out by just giving my quick spiel about why we should care about antiferromagnets, since they're sort of a big deal these days in our community. So here's, I guess, my list of reasons why I think they're interesting. So number one is they exhibit really fast magnetic dynamics. So typical frequencies of these things are in the order of 100 gigahertz or even higher, which, as compared to ferromagnets, which are typically somewhere around 1 to 10 gigahertz. So these materials are radiation hard. They're robust against external magnetic fields. So from a device, from a memory storage point of view, that's a very nice property. And then the flip side of that is that they don't really generate any kind of net dipole field. So with ferromagnets, of course, these dipole fields become problematic as you want to scale down to smaller and smaller devices. But of course, they're not really a problem with antiferromagnets. And then the last thing that I like to add is that at high frequencies, you see a linear Magnon dispersion, at least if you stay away from the edges of the Brillouin zone. And so from a signal transmission point of view, actually, it's a really nice property. So that's my list of reasons. So let me jump to a couple of papers, which I sort of just kind of randomly selected, which have come out over the past couple of years, measuring spin transport in antiferromagnets. So this one is a stack. It's like basically a trilayer with a ferromagnet, antiferromagnet, metal trilayer. And then you put a temperature gradient across the stack, and you measure the spin current that enters into a normal metal detector by inverse spin Hall effect. And then here's another paper, which is I'm going to talk about in a little bit more detail a couple of slides from now, but it's measuring an antiferromagnetic spin-Seebeck effect in an insulator in the presence of a magnetic field. So as you can see, with both of these papers, you either need a magnetic field or a ferromagnetic layer in order to realize some kind of spin signal, because of course you need to define a spin direction because antiferromagnets lack any kind of net magnetic order. So the basic question that I want to address in this is it possible, well, how is it possible to realize Magnon transport in antiferromagnets without either using a magnetic field or a ferromagnetic layer? So there's already been a little bit work that accomplishes this, so I at least want to acknowledge it. So for example, you can realize this type of spin transport in materials with broken inversion symmetry. So here I have a couple of papers on honeycomb systems. So this one proposes to realize a spin-Nernst effect in sort of a honeycomb lattice. So it's a spin-Nernst effect of Magnons. So this is from last year. And then there's this one, which is just out, which I have to admit I'm a co-author on, so I'm a little bit biased. But this is in a honeycomb lattice, which is a conductor. And it's a piezo spintronic effect. So it's the spintronic analog of a piezoelectronic effect. So under a time-dependent strain, you actually can show that you induce counterpropagating piezoelectronic effects. So you get a net spin current perpendicular to the strain. Parallel to the strain. So in any case, but what I want to talk about in this talk is transport through heterostructures. And I want to focus on this heterostructure. So you have an insulating antiferromagnet with two metallic contacts. And I want to think about biasing the structure two different ways. So number one, by applying a temperature gradient across the structure. And then you quantify the spin current that exits through one of these contacts, into one of these contacts through the spin-Seebeck coefficient. Or you can, by spin Hall effect, generate a spin accumulation, which injects Magnon current into the antiferromagnetic insulator, and then that exits out the other side. And you can quantify this by the structural spin conductance. And so basically, my talk is going to be about how to calculate these two different structural constants from a stochastic LLG model. So the take-home messages of the talk, well, I have two of them. So number one, it's possible to realize a spin-Seebeck effect, at least in theory, without the use of a magnetic field if you break the sublattice symmetry of the antiferromagnet at the normal metal antiferromagnetic interface. So number two, so you don't need a magnetic field, of course, in order to realize spin injection by spin Hall physics. But it doesn't hurt. And in fact, if you ramp up your magnetic field close to the spin-flop transition, what you actually see is a diverging conductance. So you see a huge signal of spin transport. So I think that's pretty neat. So here's the outline of the talk. So I'm going to give a brief overview of antiferromagnets and how I'm thinking about these classical Heisenberg antiferromagnets. And then I'm going to jump to stochastic dynamics in these heterostructures with a brief detour into some quantum mechanics just so that we understand spin transport, the microscopics of spin transport across these interfaces in a little bit more detail. And then I want to apply the stochastic theory to ballistic, well, I guess really quasi-ballistic transport through this heterostructure under the presence of these two types of biases. So I'm just thinking about a bipartite antiferromagnet, which is collinear, so there's no magnetic frustration. So it's pretty much the simplest antiferromagnetic system you can think of. So you can coarse grain this into the 2 degrees of freedom, which are the magnetization, smoothly varying magnetization, the smoothly varying Neal order. And then, typical thing, the standard thing that you do is you construct a Ginzburg-Landau type free energy out of a set of symmetries. So for example, if I have time reversal symmetry, which sends the Neal order to minus the Neal order, magnetization to minus magnetization. And if in addition you have sublattice symmetry, so this corresponds to switching of the two sublattices. So if you have those two symmetries, plus let me also impose just rotational symmetry about one of the axes, just to keep the discussion nice and simple. If you have those three symmetries, so these two plus rotational symmetry, you can construct a free energy that looks like this. So this has 3 terms. So the first one is the exchange stiffness, which just suppresses magnetization. So chi is usually 1 over chi is usually a large energy scale. You have in the large exchange limit. You have Neal order exchange stiffness, and then you have a uniaxial anisotropy, which in general can be any sign, but I'm just going to focus on positive k, which corresponds to an easy axis antiferromagnet. And this allows me to define a degenerate ground state. Of course, you can apply a magnetic field and break the time reversal symmetry. But in that case, it's pretty easy to see what the contribution to the free energy looks like. It looks like this. OK, so under zero magnetic field, of course, I have a doubly degenerate ground state, either in the plus, Neal order points in the plus d direction or the minus d direction. If you apply a magnetic field at 0 temperature, you break this symmetry. So now I have one ground state, but basically nothing happens. So you can keep increasing the magnetic field until you reach a critical value of the magnetic field, which is defined by the anisotropy and the susceptibility here. And basically what happens is your ground state corresponds to the Neal order flopping over, like in plane like this, and then canting slightly towards the magnetic field. So you enter this sort of paramagnetic phase called the spin-flop phase. So in this talk, I'm actually going to stay away from the spin-flop phase. And the reason for this is if you're in the spin-flop phase, you basically have an easy plane antiferromagnet. And so if you, for example, apply spin accumulation perpendicular to that Neal order, you'll induce coherent magnetic dynamics. So you get this sort of antiferromagnetic superfluid story that Cecilia was telling us about a few days ago. So I want to focus on thermal magnon transport in this case, which means that I'm going to stay in the so-called antiferromagnetic phase. So if I look at excitations around this ground state under zero field, I have 2 types of excitation. So I have a band structure that basically looks like this. So they have 2 magnon bands, which are gapped by the anisotropy here. And these 2 bands carry, there's particle hole symmetry, so they're sort of degenerate at zero field. And they carry opposite spin. So now you can imagine if you apply a temperature gradient to the system, I get 2 spin-Seebeck effects, 1 for each of these 2 magnon bands. And so I get a flux of magnons, which is sort of the same for each band, but they have opposite spin, so I have canceling spin-Seebeck effects. But if you apply a magnetic field, you break the symmetry, and you get different spin-Seebeck coefficients. So you get different transport coefficients for these 2 different bands. And now, under the application of a temperature gradient, these 2 spin currents no longer cancel each other out, and I get a net spin current. And so this was the idea behind a couple of papers that came out last year. So one is theoretical, one is experimental. And basically, so they're the same kind of system. So you take an antiferromagnetic insulator with 1 normal metal contact, apply a temperature gradient, and measure the spin current impinging into the normal metal by its inverse spin Hall current. So if you plot that as a function of temperature, at 0 temperature, I have no signal because I have no thermally activated carriers. if I increase the temperature, I actually get some peak, and then as I keep increasing the temperature, it turns out that the signal actually dies off completely. And so that's what's predicted in this sort of diffusive theory in this paper, and this is what is measured in this experiment here. And I'm going to come back to this picture later in the talk. So let me now think a little bit about how to describe classical antiferromagnetic dynamics in order to sort of probe the physics in these heterostructures. So if you just want to start out sort of the most basic thing, if I'm looking in the bulk, my equations of motion for the Néel order and magnetization, they have coupled nonlinear equations, and they look like this. These are deterministic. Here, F's are just effective fields, so they're derivatives of the free energy. But of course, the dynamics don't take place in vacuum. There's all sorts of fluctuations around, for example, phonon-magnon interaction. And we can model this by introducing stochastic terms, so Langevin forces. So I have basically effective torques that act on the Néel order of the magnetization. So here, these little f's are randomly fluctuating fields. And of course, if I'm putting energy into the system by these randomly fluctuating fields, I need some kind of mechanism to drain the energy. So I need to introduce dissipative terms, which come in the form of these. So these are basically like the antiferromagnetic Gilbert damping here. And you can, of course, just connect the strength of these fluctuations to this Gilbert damping parameter here by writing down a fluctuation dissipation theorem. I'm not going to bother to write it down, but I just want to note on a technical level, we actually end up using colored noise. Usually for these kind of calculations, you use white noise. But in this case, white noise produces Rayleigh-Jeans distribution if you're looking at the equilibrium system. And we want to simulate Bose-Einstein statistics, so we end up using colored noise. So just for the so it's not, I wouldn't really say it's like a particular color. I can show you the correlator, but I don't know. Right. So it's just some generic function of frequency that looks like something like a Bose-Einstein, which is like 1 over tanh of the frequency. Yeah. In these kind of stochastic calculations these days, I think it's kind of like a standard thing that people are using now. OK, so that's it for the bulk. So now we have to ask, well, what happens at this interface transport? What happens at the interfaces? So let me distinguish between two types of normal metal antiferromagnetic interfaces. So one is a compensated interface, which has an unbroken lattice symmetry, so it looks like this. And the other is an uncompensated interface, which breaks the sublattice symmetry. So you have a little bit of magnetization here. And so I guess maybe the stupid way to think about this is to think about each of these spins as having an effective damping at the interface that describes, for example, spin pumping, if you want to make an analogy with ferromagnets. And so of course, each of these spins has this effective damping, and there's a corresponding fluctuation dissipation theorem that you can write down for that spin. So that fluctuation dissipation theorem describes random thermal fluctuations, so kind of Johnson-Nyquist noise in here, which pumps spin back into that spin. So now the point is that if I'm looking at an uncompensated interface, then the effective damping for the two different sublattices doesn't have to be the same. They can be different. And what that means is then the different sublattices will couple differently to thermal fluctuation. So now if I apply a temperature gradient across this interface, this temperature gradient will effectively couple more strongly to one of the sublattices than to the other one. And I'll inject more efficiently spin into one of those two Magnon branches than the other branch, and I'll get a net spin-Seebeck effect across the interface. So that's sort of the basic way to understand the physics, but I'll give a different way of looking at it in a few minutes. OK, so of course you can say that this is easy to write down as a theorist. What do you actually do as an experimentalist? These kind of interfaces are hard to control, hard to grow during fabrication process. They vary from sample to sample, and it's difficult to tell exactly what's going on at the interface. So one possible alternative to this is to use a synthetic antiferromagnet, so which is just, in this case, insulating ferromagnets separated by normal metal spacers, and they're coupled to each other by, let's say, by RKKY interaction. So it's basically an antiferromagnet. But the point is, well, just looking at this, you can already see that there's a broken symmetry along this interface. So you couple to basically thermal fluctuations for one sublattice more strongly than the other one. And in addition, you can control exactly what materials that you put into this heterostructure, which means that you can control more precisely exactly what the effective damping of each of these sublattice points is. And then you can grow this. So now that if you grow this in a certain way, you can, of course, realize the spin-Seebeck effect across the synthetic antiferromagnet. So let's just go back to the sort of the bulk system. So how do I quantify spin current across the interface? Well, there's already been some work done to this end, which I'll talk about in a few minutes. But I can just make symmetry-based arguments across for what kind of spin currents flow across the interface. So if I have a compensated interface, I can only write down terms which respect the sublattice symmetry. And so that, when the dust settles, just leaves these two terms here, which looks exactly like a ferromagnet. And I've just written down the real part of the spin mixing conductance, so it looks like a ferromagnet. But of course, I can also do this calculation from some kind of scattering theory and actually show that it's a real part of spin mixing conductance. And the two coefficients here have to be the same. So this is like spin transfer torque in the presence of a spin accumulation, and this is dissipation. And the two have to have the same coefficient, which you can show by Onsager reciprocity arguments. OK, so it's actually, if you're familiar with a spin transport across ferromagnets, it's really very similar. So if I break sublattice symmetry, now I can introduce terms which no longer respect the sublattice symmetry. So I'm going to call this an imaginary part of the spin mixing conductance. And so it looks like this. So just based off of symmetry arguments, then you can write down something like this. And of course, if I have thermal fluctuations, then I can write down stochastic. So I can write down Langevin terms at this interface, which OK, I do, but maybe I'm not going to go into too much detail about that. OK, so let me take a brief detour for a few minutes into some quantum mechanical calculations that I did just so that we understand the microscopics a little bit better rather than just relying on the sort of quasi-phenomenological picture. So in order to do that, let me go back to the antiferromagnetic Hamiltonian and requantize it. And also, let me put it on a lattice. And the reason that I'm putting it on a lattice is because actually lattice effects at the interface are going to be important in understanding the spin transfer across this. Across the interface. So I can quantize this Hamiltonian by Holstein-Primakov, and when I do that, I get two types of magnons, which correspond to the correspond to those two spin wave branches that I showed earlier. So you've you basically have a gap, and now so this is like the alpha branch and the beta branch, I'm going to call it. And now, of course, it's exactly the same as before, but if you go near the edge of the Brillouin zone, then you start to get band structure effects. So that's kind of the only difference in terms of the energy. OK, so now I can write down, in order to understand spin transport across this interface, let me write down just a simple Hamiltonian which couples the spins of itinerant electrons on one side to the localized spin moments of the antiferromagnet. So basically, I have some sort of spin coming in from the normal metal side, and it scatters like this. It has this spin, and it interacts with the spins over here. And I can rewrite this now in terms of these two types of Magnon operators I showed earlier. OK, so and when you do this, you get two types of terms. So one term is elastic spin transfer. So this is an electron coming in, and basically, so it feels a little bit of the magnetization, it rotates a bit, and then it goes back to the normal metal, which is just the spin transfer torque. So it's a standard picture. But of course, it's a bit different than with ferromagnets, because in ferromagnets, there's some net magnetic order, whereas with antiferromagnets, you just feel like a little bit of the local magnetic order, and you might ask, OK, well, doesn't this sort of effect cancel out? Well, so to understand this, it's actually kind of helpful to look at the matrix element for this process. And when I do that, so here's the matrix element. So psi k and psi k prime are the incoming and outgoing itinerant electronic wave functions. And this is the effective spin density just along the effective spin density of the lattice. So of course, this is a three-dimensional integral, but these are evanescent modes because this is an insulator. So these two electronic orbitals die off very quickly. And this is really, you can think about this as a two-dimensional integral. So let me look at the simplest case, which is a totally compensated interface. So it looks like this. And so now my matrix element looks something like this. So I have this incoming and outgoing. So you can see that if I look at the in-plane component of k and k prime like this, then as I evaluate this integral over the surface of this interface, I am evaluating it over basically this term, which is oscillating, but this term is constant of the interface. And I'm adding up all the magnetization, and I get 0. So then I don't have any spin transfer in that case. But if it doesn't have to be the case that k prime in the plane is the same as k prime, same as the incoming and outgoing momentum in the plane have to be the same. So if I allow for them to be different, then you can see that this term here will oscillate at the same frequency. If this term oscillates basically at the same frequency as this term, I have some sort of rectification, and the matrix element actually doesn't vanish. And so this physically, so it has to oscillate at the same frequency actually. So this physically corresponds to these two wave vectors differing by a reciprocal lattice vector. So this is an Umklapp scattering process. So actually, So has a paper which first showed this using tight binding model and some general arguments from 2014. So I recommend checking that out. It's on superfluid transport, but this is just reproducing this from a quantum picture. And now you can actually take this Hamiltonian and you can do perturbation theory. So you do like Kubo calculation, calculate the spin current through the interface, and actually what you'll get is exactly what I predicted earlier in the talk based off of phenomenological arguments, except that now the real part of the spin mixing conductance I can actually write in terms of things that I can calculate, namely this spin mixing, namely this matrix element here. So it's a nice way of connecting these two pictures. But the other nice thing is now I can generalize this to include not just spin transfer torque, but also Magnon transport across the interface, because they're sort of similar processes. Before I do that, let me also mention, so that was all for the compensated interface. If I allow for a partially uncompensated interface here, it's like my electrons, which are scattering off the interface, see a little bit of magnetization off the interface, so it's just like a ferromagnet. And so now you can see why you get terms that look just like a ferromagnet here, except again, all of these terms are given in terms of these matrix elements here. OK. So then I can allow for, so I look at the other term, which now includes Magnon operators. So this is after I've requantized everything. So now I have spin flip processes. So this corresponds to an itinerant electron coming in, flipping its spin, transferring some energy into the bulk of the antiferromagnet, so it creates a magnon, and then returning back into the normal metal. And this process looks like this. And actually, in general, this has both Umklapp and specular contributions. So it doesn't necessarily rely on Umklapp processes. It has both. But if you go to the sort of long wavelength limit of Magnon, so Q equals 0, you'll just, and then in addition, if you go to a totally compensated interface, you'll just reproduce the physics of what I showed you on the last slide, and then Umklapp processes totally dominate. So both are present, but Umklapp processes you expect in general just to dominate at low temperatures. And also I should note, this is all for a clean interface. If you introduce disorder, that's another kind of channel that you open up in order to couple electrons on either side. OK, so what do you do with this calculation? So I can now calculate the spin current that flows across the interface. It's a long calculation, and it has a long answer. But let me just go kind of to the simplest case. So now let me think about applying a temperature gradient across this interface. And let me say that my magnons are thermalized to a local Bose-Einstein distribution function. So everything is sort of has kind of simple parameterization. And in that case, if the temperature of the magnons is strongly coupled to the phonons, so it's really locked to the phonons, and there's no temperature jump between the magnons on one side and electrons on the other side, then the spin current that goes across the interface actually has this form here. And these are basically the magnon-dependent spin conductances, which it can write in terms of these matrix elements that I showed you in the last slide. So if I take this case, so let me apply temperature gradient across my interface. And so what happens is this. So in the bulk, this temperature gradient pulls magnons of both species into the bulk. And it creates a depletion region of both types of magnons just at the interface. Now this depletion region has to be replenished by spin transfer from the bulk, from this normal metal here. So you have a spin, basically a Magnon current across the interface. But if this Magnon current, if there's a symmetry between, if you have a compensated interface and there's a sublattice symmetry, this has to happen for both Magnon species at the same rate. And so you have a cancellation of spin current. So I'm telling you basically the same type of physics as I told you earlier, but from a different kind of regime and a different perspective. And so if you break the sublattice symmetry, then the current that goes across the interface is proportional to the difference between G alpha and G beta. OK, and of course, I can use the same physics to describe spin transfer across the interface if I have a spin accumulation. It's governed by the same, basically, conductance across the interface. And there, you start to inject magnons differently. So you get an increase in magnons of one type and a decrease in magnons of the other type. So I can calculate. The point now is that I can calculate these things from a microscopic model. So I can, for example, plot the ratio of these two types of conductances as a function of this parameter here. So this JA and JB are basically the sublattice-dependent coupling at the interface between the localized moments and itinerant electrons on the other side. So they were in that Hamiltonian I showed you earlier. So when I have sublattice symmetry, I get G alpha is equal to G beta, so that's here. If I change this so that I have if I break the sublattice symmetry, then I have an increase. It turns out that it saturates at some value, or it maximizes at some value and then saturates here. And then I can plot the same thing as a function of temperature. And I'm just doing this to show you the importance of Umklapp processes. So again, at low temperatures, Umklapp processes dominate completely. There are no specular processes. But as I go to higher temperature, OK, Umklapp processes turn out to be still really important. But I open up a specular channel of Magnon transport across the interface. OK, so this is a very detailed picture of what's happening at the interface. And basically,
this is in fact processes of the electrons impinging on the interface, not the magnons.
Yes. Yeah, it's umlaut processes of the electron. So electron comes in, and then it sort of jumps perpendicular to the interface. Right? It changes momentum perpendicular, and then goes back into the normal metal. So that's what I mean by umlaut processes. So OK, so it's all a very detailed picture. Basically, I'm showing it to you just to convince you that, OK, we sort of know what's going on at the interface. But if I go back to this stochastic model, it doesn't really matter so much. I can just put in simple input parameters from this sort of a sort of simple model that I was showing you earlier. So if I go back, if you remember from a few slides ago, this is where we left off with the bulk spin transport physics. So if I now add in interfaces, it turns out that my equations look like this. Now, OK, these include surface terms. So I have terms here now that break the sublattice symmetry, just to be generic. But these terms are really localized at the interface. And the reason I've hidden some delta functions in there just to make the equations look nicer, because if you read everything out, it will make your eyes bleed. So the point here is that, OK, rather than having all these complicated microscopics, now I'm just putting in simple parameters, namely a symmetric damping at the interface. This is like this interfacial damping, and an anti-symmetric damping here. And of course, this vanishes if you have sublattice symmetry. So that's basically the stochastic model. How do you actually solve this to figure out what the spin transport is, what kind of spin transport you're getting in a heterostructure like this? Okay, of course, I take these equations, I linearize them, I integrate them over the boundary, so I get linear stochastic differential equations with stochastic boundary conditions. So in the bulk, I'm driving by bulk fluctuations, so that basically creates some kind of spin current that flows out through the boundaries. And at the boundaries, I have electronic fluctuation, which creates spin waves that enter back into the bulk. So even in equilibrium, in equilibrium, these two processes have to cancel. And actually, it's pretty non-trivial to show that they do. But I've done it, and they do. So everything looks good. And now I can apply this to several situations. Right? So let's start with the simplest situation. So let's just start with equilibrium. So in the beginning of the talk, I told you that in this type of antiferromagnet, if I'm at 0 temperature and I apply a magnetic field, as long as I'm below the spin flap transition, nothing interesting happens. But that's really only true at 0 temperature. If I'm at finite temperature, I have spin waves. And those spin waves allow for a little bit of a paramagnetic response if I apply a magnetic field. So I'll induce a little bit of magnetization. And I can calculate that magnetization based off the Stochastic LLG model, including the boundary conditions. And so this is what you get. So you get the difference between two Bose-Einstein distribution functions weighted by two spectral functions. And it's the difference between the two. And those two spectral functions are the upper Magnon branch, and the other one is the lower Magnon branch. And they have some sort of line width. And this line width now depends on the damping at the interfaces. So what's interesting about this is that even in equilibrium, if you do have symmetry breaking at the interface, you can at least in principle measure this by some sort of simple FMR experiment. So so these two different Magnon branches have different helicities. So if I were able to apply a circularly polarized FMR field with one helicity, it will couple to one of the Magnon branches, and I can measure the line width that way. If I apply a different helicity, I'll couple to the other branch. I can measure the line width of the other branch that way. And if there's a difference between the two, I can pick that up by just looking at the difference between these two frequencies on the other side. It might be a small effect, but at least in principle, it's there. OK, so now the point is, so now I've developed all this so I can apply it to, it really should say quasi-ballistic transport through this heterostructure. So now I can get on to the whole point of the talk, which is calculating these two transport coefficients. So let me apply this theory. Let me skip all of the details. But basically, from the stochastic theory, I can calculate the structural spin-Seebeck coefficient. And it turns out that when you do that and you go to the low damping limit, the peaks, so the broadening between the different Magnon modes is small enough that you can distinguish individual Magnon modes. So now the transport coefficients can be written as sums of each individual Magnon channel. And then each of these individual Magnon channels you can break up further into a symmetric piece and an anti-symmetric piece. And this you can distinguish experimentally because they transform oppositely to each other under reversal of the magnetic field. So one picks up a minus sign, and one picks up a positive sign. So that's kind of nice. So let me go ahead and for one given Magnon mode, as a function of temperature, plot its contribution to the overall spin-Seebeck coefficient. And I can do that for both the symmetric piece and the anti-symmetric piece. So if I do that for the symmetric piece, let me plot this as a function of temperature for different magnetic fields. So I can go all the way from 0 field, so I have no signal there for the symmetric piece. And I can go all the way up to the spin flop field. This is kind of my maximum value. And this peak structure should look familiar because I showed it to you in the beginning of the talk. This is what was produced from this diffusive theory and what was measured in experiment. So at least at this point, it looks pretty good. And then, of course, the antisymmetric piece as a function of temperature saturates at temperature. Actually, I should be careful there because its contribution to the total spin-Seebeck coefficient, there's also another factor of 1 over temperature here, which suppresses it. But this contribution compared to this contribution saturates. But the point of this that I'm showing it to you is that it's pretty independent of magnetic field. So even at 0 field, you can still get a finite spin-Seebeck effect. So of course, this is not what you actually measure. What you actually measure is the total contribution, which is the sum of all of these things. So now the question is, well, let's suppose that I just, again, have the simplest case where I have symmetric piece. Do I reproduce the results that were shown earlier? Yeah?
So yeah, for the symmetric case, can you explain simply why does it decrease if temperature increases?
For the symmetric case.
What's the simple reason for
Yeah,
that?
so the simple reason in this case is that it's sort of like, okay, my hand-wavy argument is that as you go to larger and larger temperature, which is much larger than the gap, it's like there's a gap between the two modes, and the gap becomes less and less important between the two. Right. OK, there's other effects, too, that will really kind of change the signal, which I'll get into later on, which will suppress the signal at higher temperature. But now, so if I take this thing, and I sum over all of the individual Magnon modes, this is what I get. So unfortunately, it doesn't look anything like what you measure in experiment. OK, so there's a good reason for this, though. And that's what I've shown you earlier in the talk. It's what I've really written down as a long wavelength theory. So there's no lattice or anything like that. So of course, it's bound to run into problems when you go to temperatures which are comparable to the energy at the edge of the Brillouin zone, right? So you're missing band structure effects, because eventually you start to saturate the signal once you get to the edge of this. There's no more Magnon modes. So that's one problem with it. Another problem is that, OK, of course, if you go to higher and higher temperatures, there's all sorts of other effects that you haven't taken into account in the stochastic transport picture. So there's Magnon phonon scattering that's not really treated properly in this. There's Magnon scattering, which is totally neglected. So you have scattering between the two Magnon branches and scattering within each Magnon branch. And that can really kind of change the signal. And then, of course, there's disorder and things like this. So there's all sorts of reasons why at high temperature you shouldn't trust the theory. But at low temperature and thin films, then basically this is what you should expect. OK. So then, of course, there's there's the other part of biasing, which is the spin biasing. So again, apply a current in the plane here, create a spin accumulation, which is collinear to the Neal order, and inject a spin current across the structure. And you can quantify it by this Magnon, basically the structural spin conductance G. And this spin conductance, just like before, if the line width is really small, you can break it up into these individual channels. And again, each of these channels, each of the contributions, you can distinguish the symmetric and the antisymmetric pieces by just changing the direction of the applied magnetic field. So it looks like this. OK. So let me go ahead and plot this as basically versus magnetic field. So it looks something like this. So this is the total coefficient. So I've already summed up all of the individual Magnon modes. So if I go to 0 temperature, I get no signal because, of course, I've frozen out all of my carriers, so nothing happens. As I go to higher and higher temperature, of course, I get larger and larger signal, so no surprise there. But what's interesting, though, is if you look at this is plotted versus field. And if you go close to the spin flop transition, what you actually see is a divergence in the signal. So you get this huge, you basically get the spin resistance of the antiferromagnet just drop to 0. And there's a simple way to understand this. So of course, I'm not quite at equilibrium, so I can't describe my spin waves by a Bose-Einstein distribution function. But I'm really close, so you can maybe approximate it that way. But as I go really close to the spin flop transition, I'm closing the Magnon gap. And if I close the Magnon gap, my Bose-Einstein distribution has an infrared divergence at low energy. So basically what you have here is you just have a ton of low energy Magnons available for transport, which flow across the channel and give you 0 spin resistance. So that's pretty interesting. Of course, then there's the problem of, well, what do you actually measure in an experiment? And so in an experiment, what you would probably do is you would have some sort of, at least for the spin biasing case, you would have some sort of spin Hall, inverse spin Hall setup, right? So just like these ferromagnetic experiments. And so you so you inject spin current by spin accumulation here, flows through this layer, and then is picked up as an inverse spin Hall effect. So you basically, it's like a non-local drag experiment. And so usually the way that people will sometimes kind of quantify the efficiency of this process is by looking at the induced spin Hall voltage, V, divided by the applied current I, and so this is called the non-local resistance. So I crunched through some numbers in this case, what you get in this case, so you do it for a platinum, let's say manganese difluoride platinum heterostructure, which are kind of popular materials these days. If you go right up near the spin flop transition, what you'll get is a resistance that's on the order of milliohms. So it's actually pretty comparable to what you would see in a ferromagnetic non-local conducting experiment. Okay, but of course, so the reason for this, so I basically, in this case, I have 0 spin resistance in this antiferromagnet. But but of course, the whole structure has a sort of finite spin resistance. So it's just like a superconductor, right? In a superconductor, even if you have a perfectly conducting superconducting element, your metallic contacts come with some finite resistance. So when you actually try and measure it, you'll still get a finite resistance. So it's the same case here. So I still have a finite resistance, and this is what basically will give rise to this milliohm in this case.
This estimate is close to the spin flop transition?
Yeah, this is close to the spin flop transition. So it's actually really dominated by the spin Hall physics. So I basically solved a spin diffusion model in these two platinum to give you that.
You know how high is the magnetic field?
Yeah, so well, so you don't need to put it in specifically for the model, right? Because then you just get. But so for manganese difluoride, I think the value of the critical field is somewhere. Okay, if I remember correctly, it's like somewhere around 910 Tesla. So. Okay. So for a spin-Seebeck effect, then you would do something similar. So you have, let's say, the same heterostructure platinum, manganese difluoride platinum. Apply a temperature gradient across here. So then I calculated or I estimated the spin Hall voltage that you would induce in this metallic contact here. Let's say for the case of, I think it's 10 to the minus 3, if I'm not mistaken, 10 to the minus 3 Kelvin applied over, let's say, 100 nanometers. So this is for a really thin antiferromagnet. And in that case, you'll see a voltage induced that's on the order of microvolts, which puts it in the same ballpark as the spin Hall experiments that were conducted in thick films that I showed earlier in the talk. Okay, so that's basically it. So that's the story of stochastic spin transport and heterostructures. So let me just mention again. So this is really applicable for thin structures, which are quasi-ballistic. So these are structures in which the magnons are not in some kind of local equilibrium. But of course, the experiments that I showed you earlier are probably in the regime in which you sort of have diffusive transport. So there's some crossover between quasi-ballistic kind of stochastic transport and some sort of drift diffusion theory. And the question is, what is the length scale that dominates? But it's actually a pretty complicated question because there are lots of processes, as I mentioned earlier, that determine that. There's magnon-phonon scattering, magnon disorder scattering. There is magnon-magnon scattering, which is even more complicated than on ferromagnets because you have 2 branches now. And these all have some sort of intricate dependence on the magnetic field and the temperature. So determining basically these time scales and length scales that determine whether you reach some kind of local equilibrium is a pretty complicated calculation, which we're working on right now. So, okay, so that's it. So.